Hi, let's see how to perform normality, or rather how to check normality of any dataset that you have on Python. Or here I'm using Google Colab. You can use any other IDE, VS Code, Jupyter Notebook, or any other that you are comfortable with. Uh, uh, let's start with importing all the necessary libraries. Uh, Import pandas, numpy, sci-fi stats, matplotlib, and skewness and kurtosis. Sci-fi.stats import skew and kurtosis. Either you can click on this or you can click Control plus Enter to run any command. Now we imported all the required libraries. Let's generate a random data, random. NP calls numpy function, sorry, library seed. You can choose any number here. I'm choosing 42. So what happens with this code is it every time you run the code, it doesn't it keeps the set of data static, not change every time. This sets the seed. Now let's create the data dot random rand int 12101 size is equal to 100. So here this creates random integers from 1 to 101, and it gets such 100 numbers. Sorry, this is a typo. np.random. Now you have your data of 100 size. Let's create a QQ plot. Plot figure fixed size. You can choose any size you want. I'm choosing 6 by 6 plot. I'm calling stats function. From that, prop plot. Data is our data. Distribution is normal. So norm plot is equal to PLT. See, this is our uh, randomly generated data. Dist is it compares our data with the normal distribution here. Now let's give a title to the plot. it gives a grade and it prints the plot. Now see, this is the blue dots are our data and red line is the data that compares. That is the distribution, normal distribution. So our data is mostly along the line, red line, so that we can say the data follows a normal distribution. Another way is to check skewness and kurtosis. So skewness is, since we already imported skew, you can directly use that. And similarly kurtosis. Here just write Fisher test as false. Just let's not go into theory for now. Just see uh, uh, how it works. Skewness is data skewness. Similarly, kurtosis data kurtosis. Yeah, this gives us skewness and kurtosis values of our data. So, for any data to be a perfectly normal, skewness should be close to 0 and kurtosis should be close to 3. Now that our data skewness is minus zero point 0.2 and kurtosis is 1.8, we can say that okay, the data is approximately following the normal distribution. It is not completely uh, not normal. Another test is we can perform a Shapiro-Wilk test for normality. Shapiro test is equal. We'll call again stats Shapiro and call the data. Print Shapiro-Wilk test colon W is equal to Shapiro test statistic and our p-value is Shapiro test dot p-value 0.4f. This gives us the results of Shapiro-Wilk test. Shapiro statistic is 0.9 and p-value is 0.03. So p-value is less than 0.05. We can say that we can reject the null hypothesis. We can reject null hypothesis, which is the data does not follow normal distribution, and we can say that there is an evidence towards alternate hypothesis, that is data follows normal distribution. Another test we can perform PP plot. For this you need to make some calculations. First, sort the data. You need to sort the data. You can do this with NumPy. Then you need to calculate probabilities. NP dot from NumPy you can create probabilities line space 0.01, 0.99. Your length is sorted data. Now what does this formula do? So it generates expected cumulative probabilities. So and now we need theoretical cumulative distributive function as to compare this or R data. Stats norm cumulative distributive function CDF use sorted data. This calculates the cumulative probabilities for a normal distribution. Scale or standard deviation of the data. Now let's plot this. Figure fig size is equal to 6 by 6. Scatter prop theoretical CTF. Let's give a color and label. Line style again color. 45-degree line. Now let's give a title to this. PP plot. Label x-axis label, x label, expected cumulative distributive function, y label, observed CDF. Now this gives, let's give a legend and a grid. Let's see the plot. This is another way to check the normality of our data. On x-axis we plotted observed CDF, that is our actual random data that we generated. This is the theoretical expected CDF that we you calculated from here using the stats library. And we plotted the same. So here we can see that this red line is the expected uh, 45 degrees line. So the data, our data points are closely following on the 45 degrees line. Hence we can say that the data follows a normal distribution. Finally, we can perform another test, uh, that is chi-square goodness of goodness of fit. Chi-square goodness of fit test. So we have to create bins of data. For that you can use NumPy. So you can give a bin size, but here I am giving auto bins. Now we need observed np dot histogram bins equal to bins. So np, it counts data points in each of the bin. Now let's calculate expected frequencies. So here we take the length of the data, stats norm.cdf, it gives the cumulative probabilities for normal distribution in each bin. Let's calculate each bin. Stats.norm.cdf bins, first bin, this is the mean of the data, and scale is equal to NP, standard deviation of the data. This minus, this is the last, let's take the last bin. Scale is equal to NP dot standard deviation of data again. Now we have the expected frequencies. Now let's normalize and we calculate expected frequencies and scale those to the total number of observations, that is length of data. And let's normalize the expected frequencies. Expected is equal to expected into observed minus expected observed dot sum by expected dot sum. Chi-square stat will be observed minus expected to divide by expected. You can check the formula of chi-square to understand how I'm writing the code. Chi-square p-value stats chi-square observed f expected is equal to expected dot p-value. Let's print our results. F chi-square goodness of it test. Chi-square is equal to chi-square stat and p-value is equal to chi-square p-value 0.4f. Histogram spelling. These are all typos. So now you got your chi-square and p-values, chi-square stat and p-value. So p-value here is p-value is less than 0.05. So we can say that we can reject H naught, I alternate, and we can say that evidence is found towards alternative H naught, H1, that is data follows normal distribution. So now we have seen around 5 ways how to check the normality of the data. So I mean, you don't need to perform all these tests to check the normality of the data. You can choose any one or two and just uh, demonstrate that your data follows the normal distribution. Um, no need to perform all these tests in your analysis. Further, let's say if your test is not following the normal distribution, you don't need to worry about that. You can perform some kind of transformations on your data, like log transformations or square root transformation or any other advanced transformations you seem fit. Uh, you think that are fit for your data, you can apply those transformations and go ahead with the applying parametric tests on your data. If your transformations fail, you can still use the data and perform non-parametric tests like chi-square test uh, or man-Whitney U test, something like that. Instead of T, Z test or ANOVA, those are parametric tests. Instead of those, you can perform non-parametric tests. Although, I mean, most of the times in real life, your data is not perfectly normal. So, but still, you will go ahead and perform your parametric test. That is because here, in such cases, central limit theorem comes into picture. Central limit theorem says central limit theorem says if the data is large enough, let's say a minimum size is 30. If it is more than 30, the data follows the normal distribution. So using this theory, you can go ahead and still perform your parametric tests. So yeah, I mean that's what uh, checking normality of your data on Python. Thank you.